One of the big concepts in related rates is the idea of a time derivative. So if I have two variables, let's call them x and y, and they may be related to each other somehow, but they're both differentiable functions of t, then what I can do is the derivative with respect to t of x is just dx dt, right? That's the definition of how that works. And the derivative of y with respect to t is dy dt, which is simple enough, right? You just sort of write them almost like it's a fraction. But what happens where I don't just have x or I have y, maybe I have y squared, or maybe I have cosine of xy or something like that, right? Well, in that particular case, we say that the derivative with respect to t of a function of x, it follows from the chain rule that you take the derivative at x, and then you, by the chain rule, take the derivative of what's inside, which is the derivative with respect to t of x. So you end up with this dx dt. In practice, what that means is you take the derivative of x just like you're taking it with respect to x, but then you slap on a dx dt at the end. Similarly, if I have a function of y, I take its derivative at y. So I take the derivative as if it were just a function of y, and then I put dy dt on the end. And that sort of helps us smooth out some of these problems, and by using this, we can approach issues. Now, one thing that's going to be different about time derivative problems is you're going to need additional information, because you now are dealing, if you have x and y and t, you have kind of three variables that you're juggling. So you need to know some information about what's going on at a particular time step to understand what's going on in the problem totally. And you'll see what I mean in these problems here. So if I am given a relation xy equals 6, then I want to find the derivative of y with respect to t when x is 4 and when I know the derivative of x with respect to t is 13. So notice I was given that information. So let's go ahead and use this. If I take the derivative with respect to t of both sides here, well, the derivative of a constant with respect to any variable is always 0. So that's going to be 0. And this is a product, so that tells me it's the derivative of the first, hold the second, plus the first derivative of the second equals 0. So now that I've performed the differentiation, what I need to do is I need to look at the original problem and see what I can't pull from there. So I know that x is 4, and I know that dx dt is 13, and I know I'm solving for dy dt, but that still leaves me to figure out what y is. Well, to do that, what I do is I look at the original equation. If x is 4, that tells me that y is 3/2. So I have to solve for that additional information. Now, doing that, by plugging in, I get 13 3/2 plus 4 dy dt is equal to 0. And so then what I can do is I can divide both sides by 4 and subtract on the other side, and I get that dy dt is negative 39/8. So that tells me part A. Now the nice part about part B is that we really have done all the heavy lifting. We've already performed the derivative here. We already have this piece. So we need to solve for dx dt. We're given 1 and negative 9. So if x is 1, that tells me that y has to be 6, because it's by the original equation. So plugging in, I now get dx dt times 6 plus 1, negative 9, is equal to 0. So subtracting I get 6 dx dt equals 9, or dx dt equals 3/2. So again, this is really the hardest part. Once you've done this, both of these pieces kind of fall out. Now, for this particular problem, we have to be a little more careful. So when we take the derivative of both sides here, so this over here is nice. We just know it's dy dt. But over here we have d dt of the square root of x. Now, if this was if it was the derivative with respect to x of the square root of x, we know that that derivative is 1 over 2 square root of x. And we know that because this is x to the 1/2. It's by the power rule. We bring the 1/2 down, and then we subtract 1 from the power, right? So if I had x to the 1/2, this comes down, and then we subtract 1, so you're left with 1/2 x to the negative 1/2. And that leaves a 2 in the denominator. The negative part puts that in the denominator, and x to the positive 1/2 is the square root of x. So that's how we get that. So then we know that x is 64. So if x is 64, then well, that tells me what y is, but guess what? Don't really need y. By the way, we get this dx dt here. Don't really need y. Now, we could solve for it. We know that y is going to be 8 here. But that doesn't necessarily we don't need it. It's good to have, but we don't need it. So in this particular case, we're given that dy dt is 9. And we're given that x is 64. So that's 9 equals 1 over 2 times 8 dx dt. So that's 16. So by multiplying, I get dx dt is 144. And ultimately, that's just the process. That's how you do it. And we're going to do some more examples to really solidify that knowledge.